Welcome, everybody. It's my pleasure today to introduce Alexey Balitskiy, and he'll be telling us about Urysohn width.
Hello, everyone. Thanks a lot for having me here. So the topic I'm going to be talking about is based on my thesis, PhD thesis, which I defended at MIT under the supervision of Larry Guth, who many of you might know. All right, I'm gonna make it like a very survey style type of talk for general audience. So I prepared more slides than I needed to, so I'm gonna skip through some of the slides depending on your interests, maybe. So you can, you can tell me about your preferences. I'm happy to be interrupted at any time. Yeah. So, okay, let's go. So I'm going to be talking about the Urysohn width, or sometimes just width. So in order to define it and motivate the definition, I'm going to go back to the very beginning of the 20th century and remind people what the topological dimension is. Okay, so throughout my talk, X is going to be a compact metric space. In most applications, it will be Riemannian manifold, compact Riemannian manifold, but for now, it's just a compact metric space. And I would like to define the topological dimension of X. So the definition that goes back to at least Brouwer and other people, which was actually defined in several equivalent ways. This is just one of them. This one was suggested by Lebesgue, apparently. And according to this definition, we say that the dimension of our space is at most D if for any epsilon, arbitrarily small epsilon, you can manage to cover your space with small open sets UI, such that no point belongs to D plus 2 sets, where D is our upper bound for the dimension. So that's what written on the slides. That's the definition of the dimension. So then the dimension, like once I define the upper bound, I say that the dimension is equal to the lower bound of those non-negative integers D, such that this holds. So yeah, this is just a very usual dimension that we are all used to. Just to give a trivial example, here is a square with the inside. So it's supposed to be two-dimensional. So let's figure out this dimension according to this definition. So first of all, I can given any epsilon, I can cover it by small sets, green sets in this picture. With multiplicity, most 3. When I say multiplicity, I mean that every point belongs to at most this many sets. So this proves that the dimension is at most 2. I can do similar picture for arbitrarily small epsilon. But then if I reduce the multiplicity, and if I try to cover my square with sets with so such that every point belongs to those 2 sets, I will fail to do it with arbitrarily small epsilon. So that's my attempt. So that's a covering with sets with multiplicity at most 2. But as you can see, those sets are not small. So, and in fact, it is a theorem of Brouwer and Lebesgue that at least one of those sets must connect to opposite sides of your square. So this actually motivates the definition of which was given by Urysohn, which is basically a quantitative version of the dimension in the following sense. So if we failed to give in evidence that our set has dimension at most D with certain precision epsilon, let's just find this infimmal epsilon for which we can manage to cover our set with a given multiplicity. So, and this lower bound on those, this infimmal epsilon will be called the Urysohn width. So strictly speaking, in this slide, you can see the definition that the D-dimensional width is at most W, if we can cover our metric space with open sets, such that the diameters are bounded by W, and the multiplicity is at most equals 1, as before. So I don't have a parameter epsilon going to 0. I just say that the infimal epsilon for which I can manage to do this will be called the Urysohn width. And in this example, by the theorem of Brouwer and Lebesgue that I mentioned, informally, one can prove that the Urysohn, the first width of the two-dimensional square equals its side length. So please ask me questions. Hopefully, okay, then I'm going to be assuming it was fine, maybe too trivial. Here's another equivalent definition of the D width, which is a more common one. The previous one was motivated by the topological dimension theory, but here is a more common one. So you can think of the Urysohn width as some quantity that tells you how well your space can be approximated by a d-dimensional simplicial complex. So an equivalent definition goes as follows. So you start from your metric space X, and you try to map it continuously to simplicial complex Y, so that all the fibers have bounded size. So once you manage to do that, with the fibers being reasonably small, having diameter at most W, then you can say that the fibers, then the Urysohn width is bounded by W. And once again, once I define the Urysohn width, once I define those upper bounds, I can say that the infimal W such that this holds is the Urysohn width by definition. Yeah, it doesn't have to be immediately clear why this definition is equivalent to the previous one, but it's a reasonably short exercise to check that, which in one direction, having an open cover of your set, you can postulate the nerve of this cover and come up with a subordinate partition of unity, which will give you such a mapping. And in the other direction, you can just think of those fibers. Well, you can cover the target space Y with very, very, very small open sets with multiplicity at most d+1. Since the Y is at most d-dimensional, you can cover Y with small sets with multiplicity at most d+1, and then consider the pre-images of those little teeny tiny open sets in Y. And those will be like morally, they will be like thickened fibers, something like that. So that's an equivalent definition. So a short historical note is that this definition was apparently introduced in 1923, but it was only published after the death of Pavel Urysohn by his teacher and friend Pavel Alexandrov, who was another founding father of general topology. Okay, so this is just to fix the notation so that you just see the definition once again, enjoy it, and we'll start from it, and I'll tell you about several applications and some funny things. So for now, you can think maybe it's more instructive to use the second definition. So you think of your X being approximated by at most d-dimensional simplicial complex, in the sense that you map your X to this complex in a continuous way, and you try to make the fibers as small as possible. That's the definition of the width. And another thing to keep in mind that it was motivated by topological dimension theory. So it's just a deficit in some sense. This is just like deficit of d-dimensionality. So if your space is not d-dimensional, you can measure to what extent it's not d-dimensional. You can measure its d width, and if it's 0, then it was actually at most d-dimensional. But if the width is greater than 0, then you can say, okay, then it's this close to be d-dimensional. There was a question: is there a direct proof from one definition to the other? Yeah, that's what I've just mentioned. So one direction is the construction that goes back to Alexandrov, which is consider the nerve of a covering, open covering, which is a simplicial complex, and map to this nerve using the subordinate partition of unity, subordinate to that cover. And the other way is just to cover your target space Y with very small sets and consider the pre-images. And this will give you an open cover of the original X. Awesome. So it was introduced and used a little bit in the works of Pavel Alexandrov in the context of dimension theory. There was some research done in the 50s, 70s, and 60s by a bunch of Soviet geometers, like to name one, Tikhomirov, I guess. There is a book of Tikhomirov on approximation theory, which only exists in Russian, I'm sorry, but it actually covers a lot of different types, a lot of invariants of similar flavor, which is not just the Urysohn width, but other widths as well. Bernstein width, Kolmogorov width, many other types of width. But they're all basically motivated by some kind of motivation by like approximating your space with lower dimension to an extent. Yeah, so the burst of interest, a significant burst of interest to this width started in the 80s when Misha Gromov wrote a couple of papers where in particular, he recalled this notion of width and tried to fit it in the context of metric geometry, which is the main thing that I'm doing. So I'll be mostly talking about metric geometry. So I'll say a few words about the questions I'm interested in, and you can tell me if any of them resonate with you as well. So one major piece of motivation for study of the Urysohn width before it became an interesting invariant on its own. One major piece of motivation goes back to the work of Gromov, field and Riemannian manifolds from '83, which proves the very famous systolic inequality. So it basically bounds a certain invariant of a Riemannian manifold in terms of its volume. And so here's what it says. So if you have a non-simply connected Riemannian manifold in dimension n, in dimensional manifold, you can consider non-contractible loops on this in this manifold, and you can ask yourself, what is the shortest length of a non-contractible loop? Non-contractible means you cannot deform it continuously to pinch it to a single point. So it's like topologically non-trivial. And yeah, so the question is, can you guarantee the existence of a non-contractible loop of reasonably short length in terms of the volume? This is only true under certain topological assumptions, which I mentioned here, but this is absolutely not relevant to the rest of this talk, so we might just skip this. And the reason I mentioned this is because it's known nowadays that one can actually sandwich the codimension one Urysohn width of your manifold in between the two quantities. And this is actually, I would say, this is the modern proof of this systolic inequality. It goes through this Urysohn width. So it was understood already by Gromov that the systole can be bounded by the length of the short non-contractible loop can be bounded in terms of the n-minus codimension one width of the manifold. But he posed it as an open question if the width is bounded by the root of the volume. And this was proven by Larry much later, 30 years. So yeah, so I'll just mention this theorem once again, because that's a cool theorem, first of all, on its own. And it has, you can interpret it in several ways, depending on what your favorite questions are, but we'll get to it. So basically, the point of this theorem is that many other quantities, metric invariants of a manifold, can be automatically bounded in terms of by the nth root of the volume, automatically, because it just happens in practice that many of those invariants are bounded by the width, by the codimension one width. So just one of them is the systolic, but under that additional topological assumption. This is the only place where it's the topological assumption. The inequality about width and volume holds for all manifolds. But this is not the only example. Yeah, also to show you that how I learned to write the tilde text on LaTeX. So there are many other invariants in metric geometry, which I'm not going to be talking about, but some of them might resonate with people here. One of them is the fill-in radius of any manifold, not necessarily essential. Another one also shows up in the work of Gromov, hypersphericity. Like Gromov introduces hyperspherical manifolds. So Gromov actually investigated many different notions of largeness of your manifold, which some of which are related to the fill-in radius, to hypersphericity, to many other things. So there is another width which I sort of like, because it's a version of the same way Urysohn width is derived from the topological dimension. You can derive a definition of the width from sort of homological dimensions and come up with a different notion of the width, which also seems to be interesting. So many other waist type invariants, where by saying waist, I mean that you slice your manifold in a family of lower dimensional entities, and you try to measure the maximal size of where the precise notion of size can be given in the values. What's that? Okay. So yeah, I'm not going to be. I won't concentrate too much on those guys. I'll say a few words about some waist things, waist-related things. So of some interest to the audience here might be the fact that persistent lifespans are also bounded by the Urysohn width, but in fact it's somewhat direct, because the persistent lifespans are pretty much the same as fill-in radius to an extent, and then, or at least bounded by. So this also follows automatically. Yeah, so even if you're not interested in the width on its own, and you are interested in other geometric inequalities, like bound something from above by in terms of the volume, then my point is that there is a decent chance that you can do that using sandwiching the Urysohn width between. Okay, so that was my introductory part with the motivation in metric geometry. So yeah, you'll have to excuse my the fact that I'm biased towards metric geometry as opposed to some other notion, some perhaps more applied fields where this can be useful as well. All right, so I'm going to go through several. So the plan for the rest of the talk is to go through several properties that you expect to be true for something that was inspired by dimension. And we'll see throughout the talk that many of them actually do not hold for the robust version of the dimension. So yeah, just to remind you that the definition of the width that I gave was some kind of robust version of the dimension. Maybe this is also a good spot for it to invite questions if there are any. Okay. Once again, the intuition behind the width is just I can roughly say with some abuse of language, I'll be saying that a certain space is almost d-dimensional or approximately d-dimensional if its d width is small, whatever that means. There's just one single example. So for a non-simply connected manifold and its universal cover, everyone knows that the dimensions coincide. So a reasonable question, a warm-up question, which turns out to be not that simple whatsoever. A warm-up question is to try to relate the Urysohn width of M and of its universal cover, where D is strictly lower, strictly smaller than the dimension. Otherwise, this is just interesting. Okay, so one example to think of is just, let's say, think of a two-dimensional torus, and let's measure its one-dimensional width. Then for small torus, the one-dimensional width is small, but the universal cover is just the whole plane. So, and it can be shown that the whole plane is not approximately one dimension. So at least one direction is false. Well, the other one also turns out to be false, but I'm not aware of examples below dimension 4. But I can give you examples of 4-dimensional manifolds, such that both 2-dimensional width and 3-dimensional width of the manifold itself large. But once you pass to the universal cover, somehow it becomes almost 2-dimensional, approximately 2-dimensional. Yeah, I didn't mention that the widths are monotone, obviously. So monotone in dimension. So once you increase the dimension parameter, the widths actually decrease. And so to say that UV3 is large already implies that UW2 is large. And then to say that UW2 is small already implies that UW3 is small.
Is there a reference you would recommend for these 4-dimensional manifolds? I mean, is this in your thesis, for example?
I don't think I wrote this up in my thesis, but it might be, maybe Hannah can remind me. Maybe we wrote this in some other paper, joint paper, but
somebody else asked me this recently, and I was like, well, it might be in remarks somewhere.
Right.
So the universal cover can have smaller Urysohn width.
The universal cover can have smaller Urysohn. Yeah.
Oh, that's very interesting.
Yeah.
You guys should write it up.
Sure. I have a reasonably simple example, which is written in my thesis. When you have a 2-dimensional surface, non-oriented 2-dimensional surface of large width, but once you pass to its double cover, orientation cover, the width becomes small. This is easy, but this is not about universal cover. But a similar trick actually works in this example as well, but it's more involved. So anyways, yeah, I'm thinking about writing a survey about or something. So if I do, then I will write this as well for sure. Let's go on. So another property of dimension that you might expect to be true. So this is absolutely not obvious from the definition of the topological dimension that I gave you, but this actually is obvious from another equivalent definition given by Brouwer of the topological dimension. And the following is obvious: the dimension is local. So if your metric space is n-dimensional, it means basically that next to each point is it's pretty much at most n-dimensional, something like that. So anyways, like if you know locally that for each point there is a small neighborhood which is at most n-dimensional, then the whole space is at most n-dimensional. This is what I wanted to say, right? And this is what's written in the language of the widths. So if the d width vanishes, it means that the space is at most d-dimensional, just by the definition, pretty much. And yeah, then the locality statement in the form that I would like to use to compare it with some robust versions of it. The locality statement is that if for any unit ball in your metric space, its d width is 0, then the global width of the entire space is 0 as well. So one can ask, is this true if you replace this equal 0 by something like less than epsilon? And I stated it in the more general version, the way it was stated by Larry. So I stated with different parameters of the dimension in the left-hand side and in the right-hand side, in the assumption in the conclusion. Well, here's why I did this. No, so sorry, before I say why, I just want to mention that this question is in particular was motivated by a related statement of Larry, which is an awesome theorem, which says that local volume bounds imply global width bounds. So basically, if you have, if every unit volume your, let's think of a manifold, of a Riemannian manifold. From now on, we're in manifolds. If every unit volume in your n-dimensional manifold is small volume, there exists some epsilon n dimensional constants such that if every unit ball has a small volume, then you can prove that the approximate dimension of this manifold drops. So if your manifold has small balls, then its approximate dimension is less than n. So it can be in fact approximated by something lower dimension effectively. That's a cool theorem because first of all, it implies the inequality, and it's much stronger than the inequality that I mentioned several slides ago. If you just use the fact that the volumes of unit balls are smaller than the volume of the ambient manifold, then you just get immediately the inequality that I mentioned before. Sorry, I was supposed to say that like this approximate less or equal means like less up to if the factor that depends on dimension only. So when I write UW and -1 less than volume approximately less, I mean that there is some factor Cn in front of the volume, which I don't write. So this is one reason why this theorem of Larry is cool. Another reason, which apparently I won't be talking about much because maybe it's not too applied. It's related to the notion of scalar curvature, and in particular to the macroscopic cousin of scalar curvature. So basically, there is in Riemannian geometry, people are often interested in the behavior of scalar curvature, and for example, in like the characterization of manifolds which admit metrics of positive scalar curvature. So this is some kind of macroscopic hand of some of those statements. Okay, anyways, let me. Right, so I want to say one more word which I did not write in my slides, but this theorem of Guth mentioned here, which, as I said, implies the conjecture of Gromov. This theorem was recently reproved by Panos Papasoglou by a very, very, very cool trick that deserves to be better known. And this cool trick is actual. So if you are for some reason interested in some kind of algorithmic questions about how you can estimate the Urysohn width of your given Riemannian manifold, then the proof of Panos Papasoglou apparently gives a certain. I'm not saying it's a good method, but I think a certain method can be extracted. So yeah. Let me get back to the locality of dimension, locality of approximate dimension. So if all of my unit balls are approximately Q dimensional, does it imply anything about the approximate dimension of the entire manifold? The answer is no. It's a huge no. Why? Because there is freedom in the choice of those parameters Q and Q prime, and the way it turns out to be that the strongest possible assumption with the lowest dimension does not apply the weakest possible conclusion, which is with codimension 1. yeah, as I mentioned, the first width is larger than all other widths, except for the zero width, of course, which is some kind of diameter connected components, which is not that interesting. So we estimate that we bound the largest width from above. This assumption does not apply about the global width. So there are manifolds, and here is a picture by my author, Sasha Bernikov. There are manifolds which are locally approximately one-dimensional, but globally they have complete dimension. They cannot be approximated by anything dimensional. So yeah, let's take a look at this picture. Maybe I don't want to spend much time on it, but that's a very cool example, which I think it's very, very counterintuitive. So there are n-dimensional manifolds for any n. In the picture, this is a piece of a two-dimensional example, just one part of a two-dimensional example. So if you want to get a two-dimensional example, you need to take many copies of this guy that is drawn in this picture and stack them together, like glue tops to the bottoms and front sides to the back sides for many copies of that, and then make it closed by gluing top of the whole stack to the bottom, the front side to the back side, something like that, whatever. So just the idea is that it looks like a certain tubular thing, but it's the right half of this picture can be approximated well by a certain square cubical grid, as you can notice. The left half of this picture can be approximated by a different cubical grid, which is the dual cubical grid to the first one. And the manifold managed to interpolate between those two guys in a cleverly chosen way, so that its global width turns out to be large. So in this example, the left half of this guy can be approximated well by something one-dimensional. The right half can be approximated, but the entire thing, it turns out you cannot project to any graph, to any one-dimensional space with small fibers. And the reasons for that are, yeah, maybe, so let me say just 2 words about it. So the fact that assumption holds, the fact that it's locally almost one-dimensional, as I said already, follows from the fact that you can just like project it to a certain cubical grid locally, as long as the piece of the surface that you want to project does not touch both the right side and left side. But the fact that the width of the whole manifold is actually large is a homological statement which can be proved using a certain homological trick, which goes back to Gromov, which I call fiber contraction argument. But yeah, I won't say much about it.
Can I ask a question here?
Yeah,
I want to ask a question. So for the entire manifold, how accurately can you bound the width? Like, you know, so I guess
within the factor of like 3 or 5, something like that. So within a constant factor. I'm really not able to find sharp bounds. So I don't know how to compute widths on the nodes, but oftentimes I can bound it with like reasonable precision. There was a question in the chat which I did not notice. Could you quantify large and small?
Yes.
Maybe I did.
So Alex, please feel free to jump in. But I think this was regarding the 4-dimensional. Oh, go ahead, Alex. Sorry.
Yeah, it was related to this example of 4-dimensional manifolds, for which universal cover will have small bits, and I guess
right. So yeah, maybe I just need to mention the quantifiers in the statement. So yeah, for any arbitrarily small epsilon and arbitrarily large m capital, no, not m is used, r capital, you can find 4-dimensional manifolds such that the width uw2 of m is greater than r capital, but uw of m tilde is less than epsilon.
Oh, okay, thank you. Yeah, thank you.
Okay, there are more statements in this flavor, which I guess I'll skip. But maybe I'll just say one word, 2 words. And in some cases, if we take into account the topological complexity of the manifold itself. So this one has this like very tubular, very spongy surface, right? So it has a large by 1, large fundamental group. Somehow, if you take into account the size of the first homology, then there are some bounds. Nothing here is really sharp. So anyway, so we have some partial results, some partial understanding. So some local to global statements do hold, but they take into account topological complexity as well. While the Urysohn width is only some kind of metric complexity, and like there are got to be something. There's some fusion of metric and topological complexity, which might survive this robust thing. And there might be some local statements, locality statements about that, but this is far from being understood well. Yeah. And another result is that even if you force your manifold to be topologically trivial, for example, M is just a sphere, then still with the worst dimensions here. So for example, the theorem that I stated before was with just dimension 1 here instead of this log. But if you assume that your M is topologically simple, then you can prove this weaker statement even with it's still a huge difference between dimensions in the assumption and in the conclusion. So all of the unit balls will be approximately log n dimensional, but the M-band manifold will be the complete dimension n and cannot be approximated by dimension n minus 1. Things like that. Okay, that was something about locality of dimension. Another thing that you expect to be true for dimension. And you also like feel free to tell me that this is not interesting for this audience. I'll just skip. Another thing that is that is true for the usual dimension is the following thing. So if you have an n-dimensional space and if you slice it by an m-dimensional family of certain subsets, then at least one of those subsets got to be at least n minus m dimensional. So this is very, very, very reasonable to expect, and this is true in the generality that I stated on this slide, without mentioning what genetic is. Okay, is this robust? If I replace the 2 dimensions in this picture, in this formula by approximate dimension, is this true or not anymore? Okay, so this was not true from the very beginning of the whatever, like the interest in metric geometers with notion. So Gromov came up with a fairly simple example, which I'll show you in a couple of slides, which basically tells you that you can start with a 3-dimensional cube with the usual metric, and you can foliate it by one-dimensional family of certain surfaces, sometimes singular, and each of those surfaces will be approximately 1 dimension, which is kind of counterintuitive at the first glance, at least. So, yeah, maybe this is just the drawback of the definition of the Urysohn width. You can have different takes. So anyways, yeah, the general prototype question is like, whenever this is like the general intuition behind the word waste. This is how I use the word waste. So whenever you have a mapping continuous, maybe, or piecewise smooth or something like that, that drops dimensions from a Riemannian manifold to a lower dimensional complex, can you always guarantee the existence of a fiber which will be large in some sense, one sense or another? So this example of Gromov shows this is not true if you expect it to be like literally the generalization, the strengthening of the robust version of the Hurevich theorem that I mentioned. So you cannot expect that your fibers will be approximately n minus n dimension. This is too much. Their approximate dimension might actually drop drastically. So, and just to give you another maybe piece of motivation, like in this statement, if you replace the measure of like how much your space can be approximated by one dimensional, if you replace the one width by the two-dimensional area, then there is a positive result, affirmative result by Clark-Tank, which is actually reduced to another theorem of Gromov, and it's not easy at all. But anyways, you can see some contrast here. So the volumetric estimates oftentimes behave better in terms of those properties. Oops, there is a problem with my tablet, so I cannot. We'll have to wait until it reconnects to Wi-Fi. Sorry.
No rush.
I can answer questions if there are any. Meanwhile,
Let me ask a question. So is it correct to say that the Alexandrov width, instead of looking at diameters of fibers, you're looking at the radius of fibers? And do people study this, or is it closely related to the Urysohn width? Or?
So first of all, there are two non-equivalent definitions. If you live in an ambient space and if you're allowed to take the centers of your circumscribed balls in the ambient space, or in the manifold, or only in the manifold for which you're measuring this quantity, and this will be two non-equivalent motions. Yeah, but basically there are some trivial bounds which you can like estimate each of them in terms of the other one within the factor of 2 or something like that. But apart from that, like, yeah, you know, like you might have noticed, I'm not really interested in sharp dimensional constants oftentimes. So if you're not interested in them, then these are just the same thing. If you are interested, then actually, yeah, Alexandrov width is sometimes better for some occasions. But also, I don't like the fact that the word Alexandrov width is not used in the same meaning as it was introduced by Alexandrov. So, anyways, I have some takes on that, but let's not go into that. Okay, so I'm gonna try sharing my screen again. Does it work? Can you see the slide?
Yeah, it looks good.
Okay, awesome. Yeah, let me just, a simple takeaway from this talk would be to take a look at this nice, neat construction of Gromov. So here's, in this picture, I drew one cubic cell of a large cubic ring. So this blue thing is the one-dimensional skeleton, like one small piece of the one-dimensional skeleton of a cubic ring, which can be extended to the entire R3 three-dimensional space. And the red thing inside is the part of the dual, with the one skeleton of the dual grid, which is also restricted to this small cube. So once I have those blue and red entities, I can define a function which will be defined on the entire three-dimensional space. Once I have the skeleton, the blue skeleton and the red skeleton, I can define a function, continuous function f of x, which basically equals 0 on one skeleton, equals 1 on the other one, and then interpolates continuously between them. So I wrote the definition of this function, and then I can draw a generic fiber of this function. So that's a pre-image of a certain point between 0 and 1, the purple surface, piecewise linear. Okay, then that's it basically. This is the mapping. So you can see that all the all the pre-images of points for this specific, very specific continuous map, they all look like those purple surfaces, or in the extreme cases, they become singular, either to the blue skeleton or to the red skeleton. So in each of those cases, you can see that you can easily map your tubular surface to one of these two skeletons, either the blue one or red one. So you can see, so some intuition reminiscent of that was already just in the previous example on the locality of approximate dimension. But this is like literally the mother of all examples. So this is the example number 1 to keep in mind when you want to disprove something about the behavior of the width. Right, and then I only drew just one cell, but you can extend it to R3, and then the entire R3 you can foliate by those purple surfaces, and one width of each of them will be less than the size of this grid, but yeah. And then you can take a huge cube inside this R3 and get this example by scaling down everything, for example. All right, so yeah, the prototype question was not true for when you measure the size of fiber by measuring its approximate n minus m width. And in fact, it turns out that you need to, in order to get a positive statement, you need to measure n over m dimensional approximate width, which is very peculiar. But I'm running out of time, so I will not tell you about that. So let me see. Maybe one more statement that I want to make. So yeah, some of those theorems about the width, behavior of the width, can be used in topological combinatorics if people are interested in that. So here is an example. So the following theorem of Roman-Karasov can be deduced from the behavior, the waist type of behavior of the widths, and there will be a very simple proof with just like very little topology involved in this proof. But the theorem itself it tells you that if you have a continuous mapping from a simplex, n-dimensional, high-dimensional simplex, to an m-dimensional simplicial complex, where n and m are related as in the slide, then there is a fiber, there is a preimage of a certain point, which is large in the sense that it meets a lot of faces of considerable dimension. Okay. What else do I want to say? Yeah, as always, like in questions like this, maybe sorry, I'll just go to the conclusions slide. So in those waist estimates, you can also play with this like trade-off between metric complexity and topological complexity. In the example of Gromov, the fibers have large topological complexity, but you can try to bound the topological complexity or somehow take it into account, and then like come up with different waist type of estimates. So which the 4 simplest examples I listed here, but yeah, maybe it's too technical to go through. So I decided to not to talk about scalar curvature whatsoever. And then the summary would be just that the short summary is that the d-width was supposed to quantify the deficit of d-dimensionality, but as we can see from those like counterexamples, sometimes it doesn't do well. Yeah, so I'll stop here.
All right, so before we get to questions, let's please briefly unmute ourselves and applaud for the speaker. All right, so questions for Alexey?
I have one. Hi, Alexey. Thank you very much for a great talk. So I want to ask about this conjecture, n-1 width versus filling radius. It's very interesting for our audience, maybe persistent lifespan and n-1 width of the. So can you lower bound the lifespan or filling radius with n-1 with some constant? Do you know about
Mm,
this conjecture?
there are. I think it's not well understood even for like two-dimensional surfaces. There is some understanding how filling radius is related to the filling radius is actually pretty much the same as a certain version of the width, which is not actually the width. It's in the way that the space you're not slicing, but trying to sweep it out with certain one-dimensional cycles or something like that. And yeah, but I don't think there is a clear understanding how much the filling radius is smaller than Urysohn. But it's a great question. But yeah, it's actually a really awesome question, because the filling radius also depends on the choice of the homology coefficients, but in the Urysohn width, you don't have a homology coefficients. So maybe like there gotta be a version of the width with the right homology coefficients, which will be better related to the filling radius. But yeah, that's a huge topic to explore.
Thank you.
Further questions? So I have a question. In your thesis, you survey what's known about Urysohn widths of spheres and balls, and I'll say I really find these results interesting. I guess for balls, maybe the lowest width is not known as maybe the two-dimensional width of the four-dimensional Euclidean ball.
I think so, yeah.
So the question is, I find these exact values of the widths quite interesting. I'm just learning about them. I mean, as you mentioned, in many of the results you're doing, it's most interesting only up to a constant factor. But if I wanted to advertise or motivate the study of exact values of widths, say of particular spaces like balls or spheres, for me, just because I find the question interesting is enough. But is there other motivation that you could add, or nothing additional?
I would actually redress this question to you. Like, what is your motivation behind the exact values of the why are you interested? Like, once you tell me that, then I'll be more interested in investigating this question.
The proof techniques, in particular, if they're topological proof techniques, then I find that quite interesting.
Okay. I also find them super awesome. Yeah, but those quantities are notoriously hard to even to lower bound in general, not to say anything about exact values.
Mm-hmm. All right, any further questions? If not, then thanks again, Alexey, and let me stop the recording here.